the quiet darkness of space, scattered among galaxies and drifting between stars, lie the most mysterious objects in the universe. Objects that bend light, warp time, and twist the very geometry of reality. They have no surface, no solid form, and no way out. Yet they control stars, sculpt galaxies, and anchor the structure of the cosmos. Stars look peaceful from a distance, but inside, they are engines of violence. A star exists in a constant tug of war. Gravity pulls inward, and nuclear fusion pushes outward. As long as fusion continues, the star holds itself up. But fusion doesn't last forever. When a massive star runs out of fuel, pressure drops. Gravity takes control. The star collapses in milliseconds. Its core crushed, its outer layers blown outward in a supernova. What remains at the center depends on mass. If the remnant is heavy enough, no known force can stop the collapse. Atoms break down, electrons and protons fuse, even neutrons give up. The collapse continues until matter becomes so dense, space so curved, gravity so extreme that a black hole forms. But what defines a black hole isn't the collapsed matter inside, it's the boundary around it. Imagine a sphere surrounding the collapsed core, a sphere so strange that crossing it seals your fate. Once anything passes inside, a rock, a star, a beam of light, a human dream, it cannot escape again. This boundary is the event horizon. It's not a wall, it's not a physical membrane. Nothing special happens locally as you fall across it, but from the outside, the horizon marks the point where escape becomes impossible because gravity has become stronger than the speed of light. Time near the event horizon behaves in bizarre ways. For an outside observer, you appear to slow down. Your clock ticks more slowly, your light reddens and fades. To distant eyes, you seem frozen in place, forever approaching the horizon, never quite crossing it. Yet from your own perspective, you fall in normally, unaware that the universe has stopped seeing you. This distortion of time leads us directly to the next question. What lies beyond the horizon? Inside the event horizon, space and time swap roles. Moving forward in time means moving inward in space. Once you're inside, falling toward the center isn't optional. It's inevitable. Just as you cannot stop time from flowing, you cannot stop yourself from approaching the core, and the core is where physics reaches its limit. At the center of a classical black hole lies the singularity, a point of infinite density and infinite curvature where the laws of general relativity break. But infinity is usually a sign that the theory is incomplete. Most physicists believe the singularity isn't a literal point, but a place where we need quantum gravity, a theory uniting the physics of the very large with the physics of the very small. Black holes are gateways into this frontier, but their behavior becomes even stranger when they spin. Almost every real black hole spins. Stars spin before collapsing, and angular momentum must be conserved. A spinning black hole drags space-time around with it, a phenomenon called frame dragging. Near the black hole, space itself rotates. Even if you try to hover still, space-time pulls you sideways. This rotation creates a bulging region outside the horizon called the ergosphere. Inside the ergosphere, you can still escape the black hole, but you can never remain still. Space is being dragged faster than you can resist. Strangely, the ergosphere allows a theoretical process to extract energy from a spinning black hole, meaning black holes aren't only cosmic traps, they are also cosmic engines. And speaking of engines, black holes power some of the brightest objects in the universe. Before you ever get close to the horizon, matter falling toward a black hole rarely falls straight in. It spirals, forming an accretion disk, a swirling ring of superheated gas. As friction tears through the disk, temperatures reach millions of degrees. The disk shines in X-rays and ultraviolet light. This glow is how we detect black holes at great distances, but the most powerful phenomena arise above and below the disk. Relativistic jets. Magnetic fields twist and funnel some of the infalling energy into narrow beams of charged particles. These jets shoot out at nearly the speed of light, stretching across thousands of light years. They can shape star formation, regulate galaxy growth, and broadcast the presence of a black hole across the cosmos. Black holes may be invisible, but their effects are not, and nowhere are those effects more profound than at the centers of galaxies. At the heart of nearly every large galaxy lies a supermassive black hole, millions to billions of times more massive than the Sun. Our own galaxy contains one, Sagittarius, 4 million solar masses packed into a space smaller than Mercury's orbit. Supermassive black holes grow by consuming stars, gas, and other black holes. They anchor galaxies, influence star formation, and shape galactic evolution. Yet their origin remains a cosmic mystery. Did they start as huge gas clouds collapsing? Did early massive stars seed them? Did small black holes merge repeatedly? Whatever the answer, these giants play a central role in cosmic architecture. But even the biggest black holes are not eternal. In 1974, Stephen Hawking discovered something revolutionary. Black holes aren't completely black. Quantum fluctuations near the event horizon create pairs of particles. One falls in, one escapes. To an outside observer, the escaping particles look like radiation, Hawking radiation. This radiation causes a black hole to lose mass. Over unimaginable timescales far longer than the current age of the universe, a black hole can evaporate entirely. The idea of black holes evaporating leads to one of the greatest mysteries in physics. What happens to the information that fell inside? Quantum mechanics says information can never be destroyed. General relativity says anything crossing the event horizon is lost forever. Hawking radiation appears random. So if the black hole evaporates completely, what happened to the information? Both theories cannot be right at the same time. This conflict, the information paradox, is one of the deepest unsolved problems in modern science. Possible solutions include information stored on the event horizon, holography, subtle correlations in Hawking radiation, firewalls that destroy falling matter, quantum gravitational structures replacing the singularity. We don't know the answer yet. Black holes sit at the boundary of knowledge, where classical physics ends and quantum physics begins. And understanding them isn't just theory, we've actually seen one. In 2019, the Event Horizon Telescope released the first real image of a black hole, a glowing ring surrounding a dark central shadow. That shadow isn't the event horizon itself, but the region where light is unable to escape, the silhouette of space-time curvature. Creating this image required synchronizing telescopes across the Earth. To form one virtual telescope the size of the planet, it wasn't just a picture, it was a confirmation. Black holes behave exactly as general relativity predicts. And this brings us to the final, most important question. A black hole is not a place, not a thing, not a monster waiting in the dark. A black hole is a region of space-time where gravity overwhelms all other forces. It is the collapse of matter into geometry. It is the distortion of time, the bending of light, the warping of space. It is the endpoint of massive stars, the engine of quasars, the anchor of galaxies, the teacher of relativity, and the doorway into quantum gravity. Black holes show us that the universe is stranger, deeper, and more beautiful than our intuition allows. They are the places where our theories break, where the cosmos tests us, and where the next breakthroughs in physics will be born.